especially, no.
Yeah, and to be honest, we need to figure out a way to adjust them on so they can fit on their heads.
Do you want that, like,
That
goes
longer.
here?
No. You want like an actual turtleneck? I can go
Yeah.
run up and see if we have it. We might have gotten rid of it.
If it's not any trouble.
Yeah, I'll go. You gotta put it in.
Dude, headband, that's it. Is that better?
Well, my head's too large.
Is it pinching? Is that what it is?
Yeah.
You don't want it to distract you.
No.
Does he have one, Liam? Okay, I think we have one. Go ahead and take that off. Unclip, yeah, unclip.
You ever see, like, that movie, A
Too
Christmas
small.
Story?
Take it off.
Too small.
Okay.
Mr. Ford is running you down a microphone right now.
Oh,
Yeah.
thank you guys so much.
Yeah. Oh, I forgot how much bother these things would take. Bother. Got it. Oh.
Lost it.
That's all right, Liam.
Sorry.
Preserve the batteries. We'll just put that under there.
Sounds good.
Okay.
We'll take this, unplug this, then plug that in right there.
Do we need the batteries back in?
Yeah, I'm gonna put them back in. I thought we were getting an entirely new thing,
No.
but we're not.
It's just easier to do this because it's on the same channel.
Makes sense. Make sure it's right.
Did you find a runaway, Liam?
I did. Not. I'm gonna turn this back on. That's caught in between.
Wired caught.
Yeah, I see. No, it's not. Okay. Mic test. Mic test. Mic test. Mic test. Well, there we go. Okay, Nathan. Now, strap that on to wherever you want.
Test it again. Here,
Or I can clip on your tie, too.
there you go. Here. Go ahead, just speak. Test. Say.
Test, test, test. Test, test, test.
Maybe a little bit closer to his face.
Go ahead.
Test, test, test.
There you go.
Test. All right.
Okay. You ready?
Ready.
Good. All right, please everybody settle in. I think we're ready now. We have our mic adjusted. Our third presenter will speak to us today, music popularity prediction with neural networks. Please give a warm welcome to Nathan Lenzini.
Okay, good morning, everyone. Sorry to be a mic squeaky wheel there, but I'm all set now, so thank you all for being here. I'm really happy to be here and to share with you something that I'm really passionate about. So today, I'm going to be talking about the potential of neural networks to be applied to compositional music data in a predictive manner. And I realize that's a bit of a verbose phrase, maybe a bit opaque, so I'm going to start by breaking down for you what I mean by this today. Maybe we'll start with what is a neural network? So I'm going to ask for a show of hands here, so I hope you're all feeling awake. I drank a lot of tea this morning, so I'm feeling awake. But if anyone in here has ever seen that AI-generated art on the internet, raise your hands and keep them up. If anyone's ever seen some AI art, if anyone's ever talked to ChatGPT, if anyone's ever used the Photos app in your iPhone, if anyone's ever used the Snapchat filter, okay? If you've done any of these things, if you've ever used a search engine, okay, you've probably been touched in your life by a neural network, which is more commonly known by people in the world who are normal as an artificial intelligence. So let's talk a little bit about what artificial intelligence is, what are neural networks, how do they relate to us today. So neural networks are a kind of computer program and statistical model that sidesteps some of the limitations that usually apply to computer programs and statistical models through a really creative structure that loosely mimics the way your brain works. They use these interconnected statistical units called neurons. So the way you think, you've got little neurons in your brain, they fire, they pass impulses through the brain, And through an incredibly complex combination of many, many neurons, you achieve cognition, you achieve sentience. Neural networks don't achieve cognition or sentience, but they do achieve really powerful predictive qualities. So if you think about, like, everyone here's taken Algebra 1 probably, you think about like a linear regression model. You've got your data, you create a line of best fit. It takes two parameters. You've got a slope, you've got a y-intercept. This line describes the aggregate of the data, but most importantly for our analogy here, you can use it to extrapolate. You can use it to say, here's what I know, here's what I think. This is what neural networks are really good at. This is what makes them so powerful. So for example, neural networks are really good at going from what goes in to what goes out. So if you give a neural network, say, a caption, a description of an image you want, it's going to feed out to you that image. So when you train a neural network, you show it a lot of paired examples. You show it what goes in, and you show it what comes out. And the neural network, over many, many uncountable iterations of training, it learns to go through from what goes in to what goes out by adjusting. In the case of this research, tens of millions of interconnected statistical parameters. It adjusts these parameters, and it allows the neural network to create generalized skill sets so that it can learn generally when I say I want a cat wearing a baseball cap. It knows how to give me that image because it knows what a cat looks like. It knows what a baseball cap looks like. It's internalized this in a statistical aggregate. It's very cool. So it uses these interconnected neurons. They pass through in layers. That's how these neurons work, in layers. And it mimics the structure of the human brain. And this is what is so powerful about neural networks. Neural networks are this really cool but maybe kind of scary emerging technology. And they are so impressive because simultaneously, in these last few years, they've grown really ubiquitous. And they've grown really powerful. So I knew I was interested in neural networks. I also know I'm interested in music. So I asked this initial question when I started out with my research. When I take the cross-section of the field of music and the field of machine learning, of neural networks, of artificial intelligence, what lies at those crossroads? What's there? When we combine these two fields of research, what's going on there? And I went through a lot of papers. I read a lot of studies. I spent a good semester. I'm at AP Research Capstone. So I spent a semester like reading these papers. And I refined this research question to ask, can a neural network be trained to accurately predict the popularity of a musical composition based on MIDI data? Now, I'm going to run through some of these studies real quickly just to show you how I kind of came to go from my initial curiosity to this final research question that I asked and ultimately explored with my own work. When people apply neural networks to music, they usually do it in one of three ways. And these are classifications that I created to help me sort my research. When people take a neural network and apply it to music, they're analyzing the music. They're going to tell us something about the music. They're generating the music. They want the neural network to make music. Or they're making predictions about the music. They want to say, here's this music. Here's what we know about it now. How's it going to be in the future? Is it going to become more popular? Is it going to become less popular? What kinds of things are going to happen? So I'll talk about some analytic neural networks. People use these analytic neural networks to discern which instruments are used in a composition. They can use these analytic neural networks to pick out which notes are used in a composition. They can even use these neural networks to isolate the emotional valence of a composition. So a neural network, trained properly, can look at a song and tell you, here are the emotions encapsulated in this song. Probably the most fascinating study I read did this to songs and then pulled play data from radio stations in cities and was able to, in the aggregate, compute the average emotion felt by people in various cities. It turns out people in Los Angeles are kind of sad. So that's really cool. Generative neural networks, usually a little more eye-catching. They grab the attention a bit more than most predictive neural networks, and this is because they make compositions, right? Like, that's really cool. You can describe to a neural network, I want this kind of a musical composition, and it's going to make it for you. That's really impressive. That's really cool. I would say one of the coolest studies I read that did this, same company that makes ChatGPT, that makes DALL-E 2, that makes GPT-4, all of these really impressive things. Jukebox, it's called. And Jukebox can make these realistic audio compositions. I can say, like, I want a piece that's a fusion of Beethoven and Elton John, and it could give it to me. And that's really impressive, too. But the least researched aspect, and this is where I chose to focus my research because this is just where it's a little more sparse, people just haven't done as much here yet, is the predictive aspect. So I can say to a neural network, here's this music, here's this song. How popular is it going to be in a year? Can a neural network do that kind of thing? Well, we know that neural networks can do this with news stories. If I feed the properly trained neural network a news story before I publish it, the neural network can look at that story and it can say, I know what kind of readership this is going to have. That's really cool. Can we do it with music? Well, it turns out, kind of. You can take metadata, and metadata are a set of numbers. They're not the music, but they describe the music. And you can train a neural network to take in the metadata and give out the popularity prediction. And you can also even train a neural network to take in metadata, raw audio, and lyrics to predict popularity. And there's an important distinction here. When I say raw audio or waveform audio, I'm talking about the file format in which most of the music you all listen to is stored in. So when you listen to a song, you're listening to a piece of waveform audio, an MP3, a wave audio file. It describes a sound wave. It describes the shape of the sound wave that makes the sound. It makes the music. So an audio playing device can look at waveform audio. It knows, I know how to distort the air to make you hear this song. That's what this is. And you can feed this into a neural network. But what nobody has done yet is nobody's ever said, like, well, what if I don't have a recording? What if I haven't finished my song yet? I just know like some of the notes. I know some of the chords, but I'm still writing. I'm still getting there. Maybe I've worked it out on some sheet music, but I don't have a recording yet. What do we do then? So I wanted to look at this. I wanted to say, what if we take an audio format that's a little more true to the partial composition process? Like I'm getting there. And so I employed a methodology. I decided, here's what I'm going to do. I'm going to try to train a neural network that can do this. Here's how I did this. The Spotify API, Spotify, by the way, is a great platform because they're really supportive of data science. They're really supportive of machine learning. They're doing a lot to make this kind of research possible, and that's very exciting. Spotify on their platform quantifies the popularity of every song that's played. If you've ever listened to a song on Spotify, you are part of a data point in this data set. So congratulations to all of you, and thank you very much. These popularity rankings, they're an aggregate number. Spotify assigns them internally, so it's a little bit opaque, like how they do it. But in general, they're an aggregate of how many times the song has been played and how recently those plays have occurred. It ranks them from 1 to 100. And Spotify also provides 30-second samples of songs. It's just like a free sample. You can download it. I wrote a computer program that downloaded about 12,000 of these. And I think maybe if you were paying attention at the beginning and you're still paying attention now, which I realize is maybe a bit of a stretch, you're noticing that there are some pairs here, and neural networks depend on pairs to be trained. You've got what goes in, you've got what comes out. What goes in, the music goes in. What comes out, popularity ranking from 1 to 100. This histogram here illustrates the popularity distribution in the data that I pulled in a pseudo-random manner from the Spotify API. You can see that it's got a concentrated peak around 67. 67, file it away because it's going to become important later. So this shows a general outline of what the data is like. However, there's a bit of a snag here, and here's the snag. We've got to manipulate this data because the Spotify samples, they're waveform audio, and I'm not interested in waveform audio. Waveform audio is what you get when you record, when you master, when you've expended the resources to complete the song, and the people to whom this research is targeted haven't done that yet. They're in the compositional process. I wanted to use MIDI data. Now, MIDI data is a little distinct from waveform in that it describes pitches, it describes notes, and so it doesn't describe the sound wave. It's something that you could conceivably have only very early on in your compositional process if you've written a melody and a chord structure. But no huge MIDI data set exists, so I had to create one from scratch. And I did this using a tool offered by Spotify that takes waveform audio and it reduces it to its MIDI components. And I've got some samples of what that sounds like here, and I'm going to try to play them. And I hope they don't deafen you, and I hope you don't hear nothing at all. And it sounds like you're going to hear nothing at all. OK, so this you can see the visual here, so it's good. We're good. There's a visual. This visual shows what waveform audio looks like. This is Africa by Toto. It's a little 30-second sample. And I realize that nobody really hates this song and nobody really likes this song, but the MIDI conversion process worked very effectively on it, so I chose it for that reason primarily. You can see this is the way the air gets distorted when you hear the song Africa. This is MIDI data. Those are the notes of the song Africa. If you were to play out the notes, this is what you would hear. So you can see how this process has occurred, and you can see how this data set has been created. Now, I had to train a model. This is the model. This is what it looks like. Isn't it cute? And you have to pick out your layers. You have to select how the model's going to be shaped. I picked 9 layers, and I trained the model. It goes through these epochs of training. You train it like 10 different times. It looks through the data. It looks through the data again. It looks at, here's the MIDI data, here's the popularity, how do I get from here to here? And then you test it. So I set aside about 20% of my data for testing to say, like, OK, you've never seen this before, because the way the model behaves on novel data and training data is going to be very distinct, because the data that it was trained on is stuff that it knows. It's seen it. It's looked at it thousands of times, so it knows what's going on there. But when you show it data that it's never looked at before, you are emulating the way that the model would behave in actual practical reality, right? You're saying, like, if I'm a composer, I want to feed data into this model. It's not going to be data the model's ever seen before because I composed it. So it's important that we set aside this test data so that we can evaluate how the model behaves on novel content. That's the whole relevance of this to practical application. So I had it guess. I had it make a prediction, I guess, is maybe a better, give it a little more credit there. But I feed it in this new data, this novel data that I set aside from the data set that it's never seen before in its training process, and I compared that performance against like a little opponent that I made for it that just guesses the average value of the data set, which turns out to be 58 every time. Because anyone can guess 58 every time. You could guess 58 every time. But like, can the model do any better than that? If the model does better than that, and it turns out that by mean absolute error, that's about 12% accuracy, if the model can get anything better than that, 12% error, sorry, if it can get anything better than 12% error, we know that it's doing something. So is it doing something? That's the question. And the answer is kind of, but not really. So over every iteration of the model, I trained it 5 times. I would train the model, I'd assess its performance, evaluate the extent to which it successfully completed the task, and then I'd make some changes based on my informed opinions on the type of model. So I did a few different kinds of changes. I increased the number of layers. I decreased the number of layers. I made the layers thicker and thinner. All kinds of different things you can do. You can alter what's called the loss function, which is essentially our cost function. Not as fancy as you might think. It tells the model how wrong it is. It's important for it to know how wrong it is. And the way that you tell it it's wrong can affect how it feels about things. So you can tweak this function, you can change this, you can change all this stuff, but in the end, it failed in 2 ways. The first way that it failed was a wild failure to learn anything, which is called overfitting. Basically, the model says, what is the best way that I can take this input and get to the output? And unfortunately, sometimes the model says, well, the best way I can do that is to memorize all the data. It memorizes all the training data, but if you memorize the training data, then you don't even have to figure out anything intelligent about the training data. So when you see the test data, the model throws up its hands. It says, I've never memorized this. I don't know what to do. And that's not desirable. That's what I called a suboptimal behavior. So the second way that it can fail is it generalizes too much. It doesn't memorize the training data, but it also doesn't learn much of anything. Ideally, you hit the right size model, the right size data set, those things line up, and the model pulls out meaningful features. It encodes, in the aggregate, in its many parameters, certain features of audio that make it popular. And the model failed to do this too. In fact, one iteration only would guess 67 because it was the mode of the data set. It was like, well, I got to be right as much as I can, and there's nothing in this data that's helping me to be right except the fact that lots of it happens to be 67, so I'm going to guess 67, and it did. 2,318 times. And that's why this didn't work. So let's have a little bit of discussion about this. We can't really conclusively say that this means anything about the popularity that, like, MIDI data is a correlation to popularity, maybe. We can't really say from this whether or not MIDI data is a good predictor of popularity because we're not assessing the MIDI data, we're assessing the neural network. But and we could have been a little more conclusive with the larger data set, which was difficult to amass, or more computing power. These are really computationally intensive to train. The Spotify popularity metric is a little opaque. But the big takeaway is that if you're a musician, you can't really rely on a neural network to tell you how popular your work is going to become. Popularity is a holistic, subjective phenomenon. I mean, there's some work that could be done with other kinds of neural networks. I used what's called a convolutional neural network, which focuses on little bits of the music isolated into chunks. But there are other kinds. A recurrent neural network that uses a sort of loop structure. It feeds backwards, not just forwards. There are some tweaks we could make to the neural network to try to make this more effective. But the big takeaway is that probably MIDI data doesn't really predict popularity all that much. So we should look at lyrics. We should look at artist information, metadata, audio, other characteristics, all kinds of stuff. And we should see what it is that truly governs the phenomenon of popularity. That's all I have. Thank you. And do I have time to take questions? 5 minutes? OK. I'd be happy to take any questions you have. I hope you have lots. I really am interested in this, and I love talking about it. So Okay, I see Fela. I think so. I've got a GitHub repository, and it feels kind of mean to leave it all lonely up there on the internet. So I'd really like to continue working on this. I'd like to write some thorough documentation. I'd like to incorporate maybe some community involvement in this, make this not just a thing I do, but a thing that people collaborate on. Because I think there really is some potential here, and I'd like to experiment with other kinds of neural networks as well, yes.
Do you think it would be more successful with more iterations for the AI training?
So you mean, I think what you're asking is if I trained the model more within each iteration, I trained it on the data more and more? Or if I continue to refine my design? Yes, I think there is some potential to work out more from that. I mean, the thing is, within 5 iterations, the trend that began to emerge was that the model was really struggling to isolate any meaningful characteristics at all. So I think there is a point at which further iterations would have ceased to be productive. I mean, there are people who worry that when we apply artificial intelligence to music, it removes kind of an indefinable creative human element from music. Like, I know when I make music, it's not just a statistical process. I like to play music, and it's an emotional process. It's a creative process. So I think people worry about that. I read a study where they designed generative AI, and they had these musicians use it to make music. They had composers made music with it. Real musicians played a real concert for real people with this AI-generated music. And they talked to the people about how they felt about it. And actually, the general consensus was that for the composers, the AI didn't replace their work, but it augmented their work. It helped them. It was more of a tool, a collaborator. So I think, yes, there is that potential for maybe some pitfalls where we devalue creative enterprises, but I also think there's really predominantly a lot of exciting potential to augment human creativity, to augment the human artistic experience in this way, yes.
Ooh, that's loud.
Sorry.
Hi.
Hi, Nico.
You mentioned in all the studies that you read that they had it predict other things about the music. Did A, those succeed at what they were trying to do, and B, did you use those as inspiration for how to design your neural network?
Yes. So the study that I mentioned that worked with audio and those kinds of things, other inputs, that was very successful. That had some success. And I looked at the structure used by that when I designed my neural network. They used a convolutional neural network. I used a convolutional neural network. I definitely pulled a lot of inspiration from that, yes. Thank you all very much.
Thanks, Nathan. That was good stuff. All right, we're going to begin